Assalamu alaikum warahmatullahi wabarakatuh. This is 421 CPE old plan subject. Its name is Integrated Circuit Design, and today we'll have a chapter 1 discussion or explanation, that is Introduction to Integrated Circuit Design. So let's start. Bismillah. So there is a referred book here, CMOS VLSI Design, a Circuit Science System, and it is a fourth edition by Neil West and David Harris. If you want to, you can study that book. From that only I prepared. So introduction. You know that integrated circuit means in one chip many circuits when is embedded is called integrated circuit, IC. So microprocessor, FPGA, SoC, DSP, microcontroller, all are called integrated circuits only. Inside many millions of circuits are there, transistors, flip-flops, many things are there. Now, what is the history of this integrated circuit? First integrated circuit flip-flop using two transistor built by Jack Kilby at Texas Instruments in 1958. See the size. There's a big size, not a small one. It's showing like that. So in 1958, he invented or he created a integrated circuit. Before that itself, all transistors, diodes already invented, but joining together to make one circuit, he inserted or he created a integrated circuit called flip-flops by using two transistors only. Now in 2010, when we come back to from 1958 to 2010, we got Intel Core i7 microprocessor, or we can say processor also. It's actually microprocessor this is, but we pronounce in everywhere i7 processor, i5 processor, like that. It is actually microprocessor. So in 2010, Intel Core i7, Intel company built a Core i7 microprocessor with 2.3 billion transistors and a 64 GB flash memory and 16 billion transistors in that. So it's very huge. It's the processor shape look like this. So now we are evolving very fast rate, we can say. Now how this growth rate is coming into the market? 50%, 53% compound annual growth rate over 50 years. No other technology has grown so fast, so long. So this is growing so fast that every year we are getting new microprocessor chips and advancements in the microprocessors, and package rate is increasing so fast, means more billions of transistors joining in integrated circuits. So driven by miniaturization of transistors, what happens when the transistor size is decreasing? What it results is called smaller transistor or smaller IC. Integrated circuit will be in cost, it will be cheaper, and it will be faster also, and it will take low power because size matters. When size is small, it take low power also. Only one drawback I can tell, it is not rugged one, means not the strong one, but okay. In that small size, we have some protections in that. So revolutionary effects on society. Because of the smaller, cheaper and lower in price, everyone can buy and they can use regular basis. So what is see here, annual sales, how it is there? 10 to the power of 19 transistor, 10 power 19 transistors manufactured in 2008, 10 power 19 transistors, 1 billion for every human on the planet, we can say, if we calculate like that. So every year, 1982, there is a chart up to 2008, every year, billions of US dollar they are spending. Semiconductor building it is. So it is every year it's rising like an exponential, we can say. So now invention of the who invented transistor? Vacuum tubes ruled in first half of the 20th century, right? Vacuum tubes are there in the starting up to 1950, up to vacuum tubes. You can see the TVs also, our old TVs, vacuum tube TVs only, CRT, cathode ray tube. Those are there, which are very large, expensive and power hungry, unreliable. If something happens, it will be damaged. So they're unreliable and very power consuming and expensive also, and size also big. So in 1947, first point contact transistor. Okay, transistor is invented in 1947. In 1958, I already told integrated circuit was developed, right? So in 1947, the transistor was invented by John Burdine and Walter Burdine at Bell Laboratories. So, by using this crystal, you can see in the picture, so how big it is. The transistor was very big. So now transistor types. We know the transistor types already. You know it already. But again, I will introduce that one. Bipolar transistors are there. In that NPN transistor or PNP transistor is there. These are silicon structure. Both germanium also there, but most popular is silicon, NPN and or PNP transistor. These are small current into very thin base layers. So NPN means what? Two diodes. When you connect into together, it is called bipolar transistor. Right? Small current into a very thin base layer controls large currents between the emitter and collector. So you know that base, emitter, collector, three terminals will be there for NPN or PNP transistor. Now the junction of this NPN or PNP transistor is called base, collector and emitter region. So a small current if you give, it will controls the large currents between emitter and collector. So emitter collector always have the output, and base and the collector, or base and the emitter has the input. So if you give the small thin current in the base emitter or base collector, it can control very huge currents of emitter and collector region. So this like a relay also, we can say act like a relay also. So base currents limits integration density. So the base, what the current we are giving to the base and emitter or a base or a collector, it will limit the integration density. That's it. Now another type of called metal oxide semiconductor field effect transistor. The previous one what we discussed, bipolar transistor is current sensitive, and the metal oxide semiconductor FET, field effect transistor, are voltage sensitive. So N channel MOSFET and P channel MOSFETs are voltage applied to insulated gate controls, which controls the current between the source and drain. Voltage applied to insulated gate which controls the current between source and drain, not like a bipolar. To the base we give the small current, tiny current or thin current, so that it will control the between collector and emitter currents. But here we give the small voltage to the gate, and which will control the source and drain, and it's an insulated gate. So there is a insulation between primary and secondary. It is the advantage. So field effect transistors are more advantageous for higher power applications. For lower power applications, we go for bipolar transistors only. Now, low power allows very high integration here. Here, base currents limits integration density. So, MOS integrated circuits, metal oxide integrated circuits we are using. I told you now, so field effect transistors more popular nowadays for high power voltages or high power cases. In 1970, processes usually had only NMOS transistor in 1970s, any processors. But these are inexpensive but consumes power while idle. There's a problem with this NMOS, N-channel MOS transistors will consume more power when they are idle, means they are not working also, it will take some power. So what happens, our power consumption, our bill will be high for electricity bill. So this is an example you can see. Intel 1101, which is a 256-bit SRAM, random access memory, and it is 1980s present, this one. Another one, Intel 404, 4-bit microprocessor, this one. And CMOS technology process low idle power, CMOS. N-channel MOS, NMOS technology have more power when idle, but CMOS processors take less power when they are idle. Means idle means not working. Now, what is Moore's law? Let's see. In 1965, Gordon Moore plotted transistor on each chip fit a straight line on a CMOS scale. Transistor count have doubled every 26 months. See, integration 7. What is Moore's law means? It is, you can say it is a CMOS scale. Semilog scale. You know the semilog scale, logarithmic scale we call generally. It's a semilog scale, logarithmic. See on the left side, there is a logarithmic scale. Now, how the integration is given? So in for SSI, small scale integrated circuits, 10 gates. Medium medium scale integrated circuit, we have 1000 gates. And large scale integrated circuits, 10,000 gates. And very large scale integrated circuits, more than 10,000 gates. If we have, then we call these variation, integration we call. So only 10 gates, then it's called small scale. And medium scale, 1,000. Large scale, LSI. About 10,000 gates. Very large scale is greater than 10. Anything greater than 10,000 gates, then it's called very large scale integrated circuits. So see the year how it is evolving or increasing the rate. Linear, logarithmic actually. If you take in the normal graph, it will be exponential, we can say. This is logarithmic. This is called semi-log. Now, this is up to what we can say 1975. Till 1975, this is the scale. Now, how it is checked in 1970 to 2005? How this VLSI, very large scale integrated circuit, is integrated a transistor, we can say. Integrated circuit means, what is integrated circuit? Joining many transistors in one compact circuit is the integrated circuit. All transistors available in a compact circuit is also called an integrated circuit. So basically it has a transistors. Now in 1970, how many transistors they used to have checked in one IC integrated circuit is 1000, means more than 1000 it is there. Almost. Now in 1970 to 75, how much? It is less than 10,000 almost. So what is this 808080808404? These are the chip names. Coming back to history, this is microprocessor name. It is 4004, 8008, 8080. See, in 1975, 8080 comes under here. LSI, large scale integrated circuit. Up to about 10,000 transistors we call, about 10,000 transistors we call very large scale, VLSI we call very large scale, and it evolved after 1975 only, and 8085 and 86 is the first state. Here I didn't mention 8085, but that's also there. In 1976, 77, 8086 came VLSI with VLSI, very large scale integrated circuits. Then it evolved to 80826. All are now integrated circuits only, very large scale integrated circuits only. And you can see here Intel 386, then Intel 486. Now Pentium, Intel Pentium, they started company or the microprocessor came to us in 1994. See, not much years passed, very less years passed. So in 1990, almost we got Pentium. Now then we got Pentium Pro, Pentium 2 we got, Pentium 3. In my study period, when I was studying 30 years before, I used to have Pentium 3 and 4 only, generally. Then we got Pentium Millennium. Then, because 2000, after 2000 we call Millennium. So that's why they named this as Pentium Millennium. Then Core 2 Duo we got it. Then Core 2 Duo Quad we got it, 2006. After that, you know what we got? Dual core we got, then core i3, then core i7, then core i9. Nowadays it is running. So like this, it is just improving, adding so many transistors in it. Now, what is the size of it? Now, minimum feature size shrinking 30% every 2 to 3 years. The size of the microprocessor or size of the transistor also we can say. So it is size minimizing or shrinking to 30% every 2 to 2 years is shrinking. We can say in 1970, one size is 10 micrometer. 10 micrometer rather. 10 micrometer is one transistor size. Now it is becoming 6 micro in 1975. Now it is 2015 only. I don't have data for that. We can evolve further. It is decreased. It is 22 nanometer. Nano means how much? 10 power minus 9. That much small transistor available in the market means we developed, and those, if we are size is small only, then we can join many billions of transistors in one microprocessor. So if you have to reduce the size of the microprocessor, Pentium 4, i7, i5, i9, then the each transistor inside it has to be minimized, has to be decreased, shrinked. So the shrinking is decreasing, shrinking is increasing 30% every 2 to 3 years. This is the important. Now, now what is corollaries? Corollaries means the graph of speed, clock speed, and is called corollaries. The many other factors grow exponentially, like clock frequency, processor performance together is called corollaries. Corollaries, we can say. So clock speed in megahertz. Now check, when in 1970 and 1975, clock speed is only 1 megahertz. Nowadays, you can see your laptop performance. It is 2 gigahertz also there, right? 2 gigahertz each core, that is. Now if we join all the i7 7 cores, then the speed will be double, like that. Speed will be that. So when these are the, in which year the processor were evolved. Now Core 2 Duo and Pentium M, Pentium 4, the shapes are there. But now the clock speed also same, it is increasing in a linear fashion based upon the processors are developed, right? So these are the corollaries about the clock frequency and processor performance. Now, what is computer aided design? CAD, we can say, computer aided design. So in 1967, Fairchild develops a micro mosaic IC using computer aided design, CAD. So designing, previously it was electronic designing was different, but by using computer itself started in 1967. Previously we have a machinery, in that we had to use some alloys we are using, and that your packaging is different, so it become problematic and slow also. But in 1967, by using computer aided design, and the packaging size become less, and the development time become less. Very fast manner we can produce the ICs. So the final AI layer of interconnect could be customized for different applications. Okay, in 1968, Neon More leave Fairchild, start Intel. So in when once the computer aided design came, the More leaves the Fairchild and start his own company, Intel. From there we got Pentium and we got i7, i5, i9. Nowadays we are getting. So like this. Now we have overview of VLSI design styles. We can basics start from IC, integrated circuit. From there we have 1, 2, 3 are there. Okay, overview of VLSI design styles. How we can divide it, this VLSI, very large scale integrated circuit is basically, inside IC, integrated circuit is there. In that we have a standard IC where we can use for microprocessor and memory protection unit, MPU, where we can use for that, and random access memory, that's also one IC, and operational amplifier. This is also one type of IC. Many are there in that basic applications I'm telling, where we are using these standard ICs. Now we have ASSP. This is applied specific standard product. This is called ASSP, means based upon the specific request only we will create one IC or design it. This is application specific, we can say, or applied specific also we can say. Application specific mostly we will say, where like codec. In this we have codec, means coder, decoder. Have you seen the cameras inside? There are ICs are there where high definition videos are stored. So how they are designed based upon the codec only, MP4 or very HVAC, different are there. So we will prepare based upon the application, that's called codec. And also local area network IC, also we can create. And USART also we can create, universal synchronous asynchronous receiver transmitter in communication. These two are LAN IC and USART IC used for communication. LAN IC is for what we call wired one, and USART is for the wireless, we can say. These are the ICs, and codec is for the video recording, means coding, decoding we can use. These are all, many are there. These are comes under application specific standard product. Now another one is there. Our part where we have to study is ASIC, that is called application specific integrated circuit. These are application specific product, and these are only standard IC, only simple IC we can say. But we need a application specific integrated circuits we are studying, in which we have many applications. So where we have based upon our request, that is programmable integrated circuit IC is there, or semi-custom IC or custom IC. So these are all application based, like nowadays small watch or car, many washing machine, any electronic applications you take, there is application based ICs only they have. So programmable IC we have again PLD, programmable logic device, and FPGA, you know it, field programmable gate array, and we have memories, PROM, OT, flash we can say. Now we have MCU, microprocessor, microcontroller unit, MCU we can say, PROM also in this it will come. Now if you go for the semi-custom IC, then we have gate array, linear array, which are used channeled C of gates, gate array, linear array we can say. So these are semi-custom ICs. Now customized IC we want, like a cell-based IC, full custom IC we have, standard cell, macro cell, means very small, only based upon the application we will use. So these are the different category or overview we can say. So next we will go for the terminology. Already I told you, but still you can have it. SPLD, simple program logic device, ROM, RAM, PLA, GAL, everything is here. I am circulating these notes. You can by heart this terminology where we use. Okay, so now if you go for the full custom ICs, we study more here because our subject is in that only integrated circuit design. Full custom ICs only we study. What is full custom IC? So in full custom IC, all mask layers are customized in full custom IC. This all mask layers. We know that IC is integrated circuit, and already you studied the PCB, printed circuit board. These are a layer formed, means so layer by layer only the ICs are integrated in one box. So the full custom offers the highest performance and lowest part cost, which is a small die size, with the only one disadvantage of increased design time, a complexity, design expense, and highest risk. Means to find the problem in that layered full custom IC, it will be problematic. But once it is designed, we know that as you go the smaller size, it will lead to smaller cost, and it will lead to greater sales. So like that, we go for the full custom ICs only. Now microprocessor were exclusively full custom only, but designers are increasingly turning to semi-custom techniques in this area also. Means they are separating one part for one application, another part for another application, like that. For semi-custom techniques also they are using. Other examples of full custom ICs are high voltage in automobiles we can use, like we got electric cars nowadays. In automobiles we are having high voltage applications also, which are converting to AC, and we are using more voltages. And analog and digital communications are sensors and actuators, where we use these full custom ICs. Makes sense for performance critical parts, or if there are no libraries available. So these are full customizes application based only, means based upon the application only we design that one. Now what is programmable logic device? We can see how the PLD will be there. Programmable are array. The this indicates the gates. These are the gates, you know it already, but indicates the circle line with the plus symbol is called programmable E connection, and small dot and with plus symbol indicates the fixed connection. Means many are the programmable here. Fixed connections are there where we cannot program, but these are the programmable connections. That's a PLD means. Now PLA, PLA, PROM, PIL, different are there, terminology already you know it. So see here, PLA is more programmable options are there, but PROM programmable options is very less, but PIL is again combination of more programmable and non-programmable is less. So like this configurations are there for PLD devices. Now what is CPLD circuit? Now CPLD circuit, we can say it having macro cells, logic block, two logic blocks, switch matrix and logic block. In this, micro cells are here inside, like the previous one I saw, PLA, PROM, PL, the programmable units. So in this also we have a programmable logic devices here, complex. CPLD means complex programmable devices, right? So we can have that one. Now what is FPGA? Field programmable gate arrays. How it will look like? This is called blue block is called reconfiguration. We can configure that one many times. We can configure reconfiguration block. So in this CLB will be there. That is arrays of reconfigured blocks, CLB, and connected by a programmable interconnections. That is called switch matrix. These are connected to the switch matrix, and these are the red boxes are called input output block. The block architecture differs from vendors, but it always LUT based, means based upon the units. Here LUT means logic unit base, even based upon the vendor logics, how they want the application, based upon that it will be designed. Now we can have a very configurable technology in FPGA, field programmable gate arrays. So basic idea is a two-dimensional array of logic blocks and flip-flops with a means for the user to configure. Means we can configure based upon the logic blocks. The interconnection between the logic blocks we can see here, and the function of each block also we can see here. See, logic block, interconnection of the configurable logic block. This is CLB, and integration we can see here. The switch matrix, this is the switch matrix where we connected here. These lines, we can say these lines are the switch matrix, and the cross point connection, this one. These are the cross point connections. So it's very in-depth knowledge we have to know, but our subject is not that much deep. Only we'll have to know what is the FPGA and how the Xilinx software we can use to configure or to program it. That's it. Okay, example of general architecture of Xilinx FPGA kit. This is the horizontal routing channel and configuration logic block and input output blocks and vertical routing channel. These are the channels, vertical, and these are the horizontal routing channels. Now if we come to XC2000 CLB of the Xilinx FPGA, old only, but I don't know. So like this, these are the inputs A, B, C, D, and we have the lookup table. Then as per that we have the gates here, and we'll give the clock here, and we'll get the output X and Y here. Okay, this is SR and D logics, what we call SR gate latches, we can say D latch, and this is the output Q, and combinedly XY will be our output. 4 input we can say here, XY is the output. We'll study, and this block is called user programmed multiplexer. These are called multiplexers, user programmed multiplexer. These are there. We can see later how it is. Now what is VLSI stands for? What is VLSI? Very large scale integration, means integrated circuit also we can say. Very large scale integration. defines integration level. In 1980s, holds over from outdated taxonomy for integration levels. Obviously influenced from frequency bands, high frequency, very high frequency, and ultra high frequency. Based upon that, they also integrated circuit design, named it. Sources and disagree on what is measured, gates or transistors. They disagree about how, based upon the gates, name is changing. But okay, based upon the gates and transistors only we named it. That is SSI, small scale integration, already explained in the previous slides. 10 power 2 means 100 slides. If it is 1000, 100 transistors. If it is gates or transistors are up to 1000, then it is medium scale. If it is 100, and this is small scale. If it is 1000 to 10 power 5, then it is called large scale. Now if it is more than 10,000, 10 power 5 to 10 power 7, it is called very large scale integration. After that we got ultra large scale integration greater than 10 power 7. By 1975, I think in the previous slides we can see, up to VLSI was designed up to more greater than 10 power 5 only, right? So now come to the top button, the flow chart, how the VLSI design flows. First, system specifications will get it, then functional architecture we will design, then again functional verification we will do, again we will loop it. So to verify proper functional architecture is designed or not. Now next we will go for the logic design based upon our system specification and functions what we are using. Then we go for the logic verification. Every time, for every step we have verification also, so that we should not fall into the false design. So logic design, then we'll go for logic verification. Again it will check for that loop if it is perfect or not. If it is okay, then we'll go for the circuit design. Once logic verification done, we'll go for the circuit design. Then circuit verification will again we'll check it again, it will verify it. Now then physical, once circuit verification done on the CAD, that is computer design, then we go for the physical design. Then once the layout physical design is done, we'll go for the layout verification. Layout verification means it's working or not, everything. Then we'll check again and again about the physical design, it's properly working or not, any errors are there, debugs are there, we have to remove it. Then we go for the fabrication and testing. Now here it will come for as per the application. Now we can go for the production. Fabrication testing is nothing but for production. So these are the flow chart we can say. Then we can have top down versus bottom up design also. Top down design adds functional detail, create lower levels of abstraction from upper levels. Bottom up design creates abstractions from lower level to behavior level. Now good design needs both top down and bottom up level. Means we have to verify what is top down and bottom level verification. Every time we have to verify what we design is correct or not, step by step. Now we'll say design cycle. System same the what we call the flow chart I showing here now. First what we did, system specification we design, then we designed the architectural design, then functional design, then we got logic design, then circuit design, then physical design, then fabrication and packaging and testing. So these are the steps followed by this one. Okay, so this is your cycle, the samples here saying. So structural design means how it is flow chart. Inside flow chart will be there, that's called structural design VHDL. Logic design means we use formulas and everything to get the outputs, to give the inputs and to get the outputs. We'll got the logic design. Now circuit design already you know, basic design, that is programming and what we call joining the transistors, and CAD only, computer design only. Now physical design. Now physical design we will make it on a chip. Physically how it will be manufactured, how much distance it has to make, and what is the space arrangement, how much power it will take. That is called physical design. Then application, fabrication. Fabrication means we are just printing it, fabrication. Then packing and testing. Once it is fabricated, then we will go for the packing and testing. This is called so VLSI design. So this is about the chapter 1. Now in next chapter we'll study about the how we use the Xilinx software and what are the libraries and what are the programs to make a behavioral uh, design. Okay, architectural design where we get the behavioral effects. Then we'll see the all the steps we'll follow to get the outputs. Okay, thank you.